Hi everyone. So I want to talk to you guys about how to recognize when am I going to draw a resonance structure. How do I know? So I have 5 little tricks to tell if a resonance structure is possible. So starting with the first pattern, if you have a lone pair next to a pi bond, you're going to have a resonance structure. And just a reminder, when we are doing resonance structures, we are only going to be moving lone pairs or pi electrons. Also, they have to be next door. So wherever you're moving these electrons, it has to be to the atom that is bonded to where the electrons are. Hopefully that'll make sense in a second. So in this example, we do have a lone pair next to a carbon that contains a pi bond. So I know off the bat resonance is possible. The way this is going to work is we are going to use the lone pair electrons to actually make a pi bond. All right, so let's look at what we just did. If I use those lone pairs and I make a double bond here, I would have this structure. But there is a problem here. Maybe right off the bat you can see it. It has to do with this carbon right there. So before we formed a new double bond, that carbon already had 4 bonds. It was happy. After, I now have too many bonds here. So I know there has to be more to my resonance structure. And what we're going to do to fix this is we are going to break the pi bond that was originally there and move those pi electrons to make a set of lone pair on the carbon at the end. So that has now alleviated, or we now are actually following the octet of the middle carbon. And that completes our resonance structure in terms of where electrons are going to go. But notice that the net charge of my beginning structure, or my resonance form A, had an overall negative charge. And resonance structures should always have the same charge no matter which structure. So here it looks like I have a neutral compound. So I know I need to check my charges. So the first carbon that I had here had a negative charge. It gave up the electrons to form the pi bond. So it now has 4 covalently bonded, or it has 3 covalent bonds, but it has a complete octet, so it should be neutral. The carbon here also has a complete octet and is neutral. But this carbon right here does not have, it has a full octet, but we know that carbon prefers to have 4 bonds. So if we go through our formal charge calculation, I know that this carbon should be negative. So I now have a net charge of negative and my resonance structures match. So this would be the resonance structure for this compound with the lone pair next to a pi bond. The next pattern is if you have a lone pair next to a positive charge. All right, so with this one, we can see that we do have a lone pair, and that carbon is going to be negative next to a carbon that contains a positive charge. All right, so what we're going to do is very similar to the previous pattern, where we're going to take this lone pair and we're going to form a pi bond. All right, so we're going to look at what we just did. So I still have my hydrogens because I am not allowed to break single or sigma bonds. I just created a new double bond, and then I did nothing else to the rest of the structure, so I'm going to leave it alone or keep it the same. So I notice here the net charge of my first resonance structure, or resonance form A, was neutral. So far it looks fine, but let's always double check because resonance form B also looks neutral. So I can see that I gave up these lone pairs, so I lost electrons on carbon. And if I look at the carbon, or how that bonding arrangement is now, I should be neutral. The second carbon, so the one that originally had the positive charge, it now also has a full octet, and it is satisfied carbon's ideal motif of where we have 3 covalent bonds, and one of those being a pi bond. So this carbon should also be neutral, and then I didn't change anything about the third one. So yes, overall this compound is neutral. So this would be the resonance structure we have if you were to have a lone pair next to a positive charge. All right. The third pattern is if I have a pi bond next to a positive charge. So this is going to look a little different because we're not dealing with lone pairs. But again, lone pairs and pi bonds are the only electrons I'm allowed to move for resonance. So I'm going to start with my pi electrons here between the two carbons, and I'm going to move this pi bond next door. All right, so that's important. I can only move it to an adjacent atom. Another way I like to think about it is this is the carbon that actually, well, it is one of the carbons that contain the double bond. It is still going to have the same double bond, but it's going to be on the other side. So that's how I know I'm not going too far. All right, I'm not jumping, or I'm not trying to push those electrons too far away to where it's not real. So the structure that I get now is the carbon on the left side is now doubly bonded to the carbon here. And then I have broken this pi bond, so I should now have a single bond on this side. And so I have a net charge of positive on the left, so I should also have a net charge of positive on the right. And if I go through, it's going to be this terminal carbon on the right side. So this would be my resonance structure for this compound, or this scenario. The fourth pattern is do I have a pi bond? If you do, you're going to be able to draw a resonance structure. And that's because I'm allowed to break pi bonds. So in this case, I'm going to break the pi bond and give this oxygen a lone pair. We know that this oxygen should already have two lone pairs. So by drawing this resonance structure, I'm giving it a third lone pair. I no longer have that pi bond, so I should have a single bond here, and now I have three sets of lone pairs. And we should recognize that oxygen with three lone pairs and one bond is negative. Okay, so here I'm starting off as neutral, but right now this looks overall negative, so I need to double check my other charges. Let's look at the carbon that originally had the double bond here. We can see that it has three bonds. I don't have any lone pairs, so that's probably where my charge is going to be, and we should recognize that a three-bonded carbon with no lone pairs should be positive. So now I have my neutral net charge that I need to be equal to the first form. And I could have pushed these electrons the other direction and put a lone pair on the carbon. We'll talk about how the idea that not all resonance structures are the same energy, or they're not all the same stability. So the reason I chose oxygen was because oxygen is more electronegative than carbon. So it is going to be more stable to have a negative charge than carbon would. But that doesn't mean you would have been wrong to draw it going to carbon. All right, it's just the idea, we just wanted a resonance structure. We didn't ask for the most stable, which is a different question. And beyond the scope of this video. And then the final pattern is that if you have a compound that all of the atoms that are in a ring are participating in a pi bond, then you're going to have a resonance structure. So this is benzene. Benzene's pretty special. We'll talk a little bit about benzene at the end of the class, and especially if you go into Orgo 2. But we can see that all of the carbons in benzene have a double bond in some form. All right, so this pattern of single, double, single, double, single is very special. And we'll talk more about that in Orgo 2. But that's a sign that I can do a resonance structure. And there's a lot of ways that you can draw this based off what we've already talked about in this video. But one of the most common ways is breaking the pi bonds and moving them over one atom. So I can take all of these pi bonds and shift them over. So the resonance structure that I'm going to draw is going to look like this. All right, I am missing my skeletal structures soon. Get all those hydrogens in. Okay, so what happens is the pi bond that was here has now moved here. The pi bond that was here has now moved here. And that third pi bond that was here has now moved here. So this is now my new resonance structure of benzene. And that's it. So those are 5 patterns that you can look for to determine whether or not you have a resonance structure.